Hi everyone. Today is Friday, April 3rd. Well, technically not, but it's Friday, April 3rd as far as we're concerned. And today we're going to look at three gas laws: Boyle's Law, Charles' Law, and Gay-Lussac's Law. And tonight we're going to have a homework assignment. We're going to try 6 problems, basically 2 of each of these types. Up here also you see that we have a test scheduled for April 21st. It's a big tentative right now. I don't know where we'll be at that point. And I'm working on this still, for our first virtual lab on gases to take place on April 14th, so about 2 weeks from now. If anyone has any questions, please remember that you can check Schoology during the Zoom session tomorrow. I'm actually going to be reviewing these 6 problems, so if you have questions, you can definitely check that out then or ask questions then, and I'll take care of those questions. Okay, before we begin today, we're going to be looking at a lot of equations. So one of the things that I wanted to make sure that I took the time to review with you is how to solve for a particular variable when you're solving an equation. So we have 2 different equations here. We're going to have equations that look very similar to these when we start the gas laws, so I wanted to show you this first. Let's take C, for example. If I wanted to solve this equation for C, what I would have to do is get C by itself, meaning I would have to get rid of B and D. I showed this to you earlier in the year. You can move variables diagonally across an equal sign. When you're done with an equation, there are 2 things that have to be true. Number 1, the desired variable must be alone. And second, and most important, the desired variable must be on top. So in this case, if I'm solving for C, I want to move B and D diagonally. So I'm going to get C is equal to A divided by B times D. That problem is fairly simple. Now, when you have a more complex equation like you have over here, and like what we're going to see today, you have to be a little more careful. So we're going to look at 2 different examples. So in the first example, we're going to solve for something on top. So let's say we solve for D. So if I'm solving for D, that means everything else that's on this side of the equation has to be moved away. So F has to be moved away. So A and B are on the top on the left side. F is going to join A and B because it's going to move diagonally across the equal sign up here. E, which is on the right side, is also going to move away. So E is going to move diagonally across the equal sign. So we're going to get C and E both on the bottom, and that is equal to D. Remember our 2 criteria. It has to be by itself, which it is, and it has to be on the top, which it is. This gets a little more complicated when you're solving for a variable that's on the bottom of an equation. So this time, I'm going to solve for the variable F. So the very first thing that you have to do is to make sure that F is on the top of the equation. Right now, it's on the bottom of the equation. That's not doing you any good. So what you're going to do first is you're going to move F up across the equal sign up here. Now you have A, B, and C that you have to move away from it. So at this point we have F, A, B over C equals D, E. I'm still trying to solve for F, so now I want to get all of these guys away. So C is going to go up, so we're going to get D, E, C. And A and B have to get away from F because we want F to be by itself. So they're going to go down here. A, B. I know that some of us struggle with this. And if you cannot solve for a variable, it's going to be a really tough unit for you because we're going to be manipulating equations throughout this entire process. If you still need more help after watching this video, watch the video again, and a second time, and a third time, and try solving for other variables. So for example, if I go back to my original equation, and just to practice something, let's say I want to solve for C. Make sure that you can do this. C is going to equal F, A, B over D times E. Make sure that you can do that. If you can solve that equation as quickly as I just did there, then you should be good to go. If not, you're going to need some more practice. Okay, I'm back with our first gas law that we're going to talk about today, which is called Boyle's Law. Boyle's Law looks at the relationship between pressure and volume. Here's the equation for Boyle's Law. P1V1 equals P2V2. It looks like one of the equations that we just saw on the previous page. Notice with Boyle's Law, we're at constant temperature. So we're going to talk a lot about three variables: pressure, volume, and temperature. And in each law that we learn about, one of those variables is going to be held constant.
Today on Sci Guys, Boyle's gas law. Welcome to Sci Guys. I'm Ryan.
And I'm Mark. And today we'll be starting our three-part series on the laws of gases. Today's episode, Boyle's Law.
Under pressure.
Just Shazam it, it'll know. Boyle's Law states that in a closed system, pressure and volume are inversely proportional. What that means is that as pressure increases, volume would decrease, and vice versa.
The only equipment you're going to need for this episode includes a large syringe that you can get at a medical supply store or drugstore,
and water balloons, which we found to work well because of their small size. Although we're not dealing with anything hazardous in this episode, it's never a bad idea to wear some eye protection and a lab coat or apron. The first step in our experiment is to blow up our water balloon. Keep in mind how large it is, as it still has to fit inside the syringe. Once you have it to a good size, just tie it off, like so, and you're ready to go.
The next step in our experiment is take your small balloon in your large syringe and drop the balloon inside the syringe and place the plunger on the end. For our first test, place the plunger at the highest point in the syringe and cover the bottom opening with your finger. Next, press the plunger down and watch as the balloon shrinks in size. Remove your finger from the bottom of the syringe to release the pressure. For the second test of our experiment, we're going to place the plunger at the lowest point it can be without touching the balloon. Once again, place your finger over the opening in the bottom of the syringe and pull the plunger upwards. Watch as the balloon increases in size. To release the pressure, remove your finger from the opening in the syringe. Let's look at this experiment a little closer. Boyle's gas law states that when a fixed amount or mass of an ideal gas is kept at a constant temperature and in a closed system, then its pressure and volume are inversely proportional. What this means is when pressure increases, volume decreases, and as pressure decreases, volume increases. An ideal gas is a theoretical gas composed of a set of randomly moving, non-interacting particles. Under normal conditions, many gases such as oxygen, hydrogen, and some heavier gases like carbon dioxide will behave like an ideal gas. This means they follow the laws of ideal gases, such as Boyle's Law. In our experiment, the balloon and syringe are filled with tons of gaseous air molecules. Placing your finger over the opening at the bottom of the syringe keeps the mass of air molecules constant and creates a closed system that will allow us to manipulate the pressure and volume. When we press the plunger down, we are increasing the pressure being placed on the air molecules inside the syringe by reducing its volume. As the pressure increases, the amount of force placed on our air molecules increases and they are forced closer and closer together, decreasing the volume of space that our gas takes up and shrinking the size of our balloon. When we remove our finger from the bottom of the syringe, we release the added pressure and our balloon grows back to its original volume. In the second portion of our experiment, we start with the plunger at the bottom of our syringe, almost touching the balloon. When the plunger is pulled upwards, we are reducing the pressure inside the syringe by increasing the volume of space the air inside takes up. This decrease in pressure and increase in volume pulls the air molecules further apart, increasing the amount of space the gas takes up, growing and expanding the size of our balloon. Removing your finger from the bottom of the syringe returns the pressure back to normal, reducing the volume and size of our balloon. When we compare the two variations of this experiment side by side, we can clearly see the inversely proportional relationship between the volume and pressure of an ideal gas. This relationship is known as Boyle's Law.
Well, that's it for episode 1 of our series on gas laws covering Boyle's Law. Thanks for watching.
If you enjoyed this episode, let us know in the comments below and subscribe for future episodes.
And remember, like us on Facebook and follow us on Twitter.
And if you have any questions related to this experiment or about science in general, let us know in the comments below or on Facebook and we'll try to help you out as best possible. Thanks for watching. Bye.
Bye.
In this first law, temperature Okay, I'm back, and I wanted to quickly recap with you what that video just showed you. So if you noticed, when the pressure was high, the volume of the balloon was low. So we're going to put a data point right here. But when the pressure inside the syringe was reduced, the volume of the balloon expanded. So at low pressure, the volume was greater. So I'm going to put another data point right here. This relationship is an inverse relationship. So at high pressure, the balloon had a low volume. At low pressure, the balloon had a high volume. All right, on the next page, we're going to take a look at our first practice problem, and we're going to be using this equation. Remember, for Boyle's law, pressure, volume is an inverse relationship. So as one goes up, the other must go down. Okay, so this is our first problem. We have a Boyle's law problem. I copied over the equation that we need up here. We'll use that in a second. When you do these problems, I want you to be writing down the givens just like you would do it in math class. So on the side here, I'm going to write down, as we go through it, each of these givens. So a gas is produced during a chemical reaction. The gas occupies a volume of 12.3 liters. That's going to be our volume number 1. At a pressure of 0.750 atm. So our pressure number 1 is 0.750 atm, again, 3 significant figures. As part of the industrial process, the pressure on the system is increased to, a trick, right? We have mmHg, here we have units of atm. They have to be in the same units. So what I'm going to do before I plug it in over there, before I list it over there, is I'm going to convert this unit. So I have 745.0 mmHg. I remember from my lesson on Monday or Tuesday that for every 1 atm, I have 760.3 significant figures, mmHg. So if you look at this relationship, 745 divided by 760 means we need to get a number that's less than 1. I'll tell you, it turns out to be 0.980 atm. That is our pressure 2. Our volume 2 is our unknown. As part of the industrial process, the pressure is increased to 745.0. What is the new volume? Now, think about this for a second. If pressure is increased, and this is an inverse relationship, volume needs to decrease. That means when we get an answer, it better be less than 12.3 liters. All right, so if I start off with my equation, P1 V1 equals P2 V2. I'm solving for V2. I need to get this guy by itself. I'm going to move P2 diagonally, so I get V2 on top and by itself is equal to P1 V1 divided by P2. Now I can plug in all my values. So my pressure 1, 0.750 atm. I'm going to multiply that by my 12.3 liters. I'm going to divide that by my pressure 2, which is 0.980 atm. If you do this correctly, your units should also work out. So notice that I have atm on top, atm on the bottom. So these guys are going to cancel out, and I'm left with a unit of liters. That makes sense because I'm looking for a volume. In this case, my volume number 2, is going to end up being 9.41 liters. Remember we said earlier, our volume better be smaller than it was before. So we started off at 12.3, we jacked up the pressure, we lowered the volume. Perfect. So here goes our second law, Charles' law. This time we're looking at the relationship between volume and temperature. Notice that the equation looks different. That's going to be a clue that the relationship might also be different. So what we're going to do now is we're going to watch another short video on the relationship between volume and temperature.
Today on Sci Guys, Charles' Law.
Welcome to Sci Guys. I'm Ryan.
And I'm Mark, and welcome to part 2 of our series on the laws of gases, Charles' Law.
Under temperature, do.
Charles' Law states that in a closed system, temperature and volume change proportionally to one another. That is, as temperature increases, so does volume, and vice versa.
The equipment we need for this episode is a heat-resistant beaker or glass,
Some balloons,
some boiling water,
and a fridge or freezer to cool our balloons in. In this experiment, we're going to be using boiling water, so for safety reasons, we highly recommend the use of goggles, temperature-resistant gloves, and an apron or lab coat to protect from spills and splashes. The first step in our experiment is going to be to blow up our balloon. Now, if you watched our previous episode, we're going to want to blow it up a little bit more this time. Like so. We're just going to tie it off like so. There you go.
The next step in our experiment is to pour boiling water into our glass beaker. Place your balloon into the beaker. In our first attempt at this experiment, we used a water balloon in boiling water. As the water balloon sits on top of the boiling water, it gradually increases in size. There's only one problem with a water balloon. They tend to pop because of their small size. In our second attempt, we used a full-size 12-inch party balloon and less water. We also placed a lid on the top to contain the hot air inside the beaker. In this version of our experiment, we see a more dramatic change in the balloon's size, as well as a much lower risk of the balloon popping. For the second portion of our experiment, we're going to place a balloon into the freezer. Leave your balloon in the freezer for a few hours. After a couple of hours, when we remove our balloon from the freezer, we'll notice it's smaller in size. As it warms up, it will gradually increase in size. Let's look at this experiment a little closer. Charles' gas law states that when a fixed amount or mass of an ideal gas is kept at a constant pressure and in a closed system, then its temperature and volume are directly proportional. What this means is, when temperature increases, volume increases, or as temperature decreases, volume decreases. As we mentioned in our last episode, an ideal gas is a theoretical gas composed of a set of randomly moving, non-interacting particles. Under normal conditions, many gases such as oxygen, hydrogen, and some heavier gases like carbon dioxide will behave like an ideal gas. This means they follow the laws of gases such as Charles' Law. In our experiment, our balloon is filled with gaseous air molecules. When the balloon is placed in the beaker with boiling water, the energy from the higher temperature water and steam molecules transfer to the lower temperature air molecules inside our balloon, exciting them. When the air molecules in our balloon are excited by raising their temperature, they spread further and further apart, increasing the volume of space they take up. The higher the temperature or the more energy the air molecules get, the larger our balloon will grow, or in other words, the greater the volume of space our gas will take up. If we remove our balloon from the hot water, the air molecules inside our balloon will gradually lose the energy they've been given, dropping back to room temperature, causing the balloon to shrink in volume back to its original size. In the second portion of our experiment, we place our balloon in a freezer, which causes a transfer of energy in the form of heat from the warmer air molecules inside our balloon into the cold freezer. As the energy is removed from our air molecules, they slow down, drop in temperature, and get closer and closer together, decreasing the volume of space they take up. The colder the air molecules get, the closer together they will be. If the temperature of a gas is lowered low enough, it will go through a change in state from a gas into a liquid. When we remove our balloon from the freezer, the air molecules inside will gradually gain extra energy from the air in the environment, raising its temperature, causing the balloon to increase in volume back to its original size. By changing the temperature of our balloon, we can clearly see the directly proportional relationship between the temperature and volume of an ideal gas. This relationship is known as Charles' Law.
Well, that's it for episode 2 of our series on the laws of gases. Thanks for watching.
If you enjoyed this episode, let us know in the comments below and subscribe for future episodes.
And don't forget to like us on Facebook and follow us on Twitter.
Okay, so hopefully everyone understood that video. The takeaway message there was that volume and temperature are directly proportional. This is exactly the opposite of what we saw at Boyle's law. So at low temperatures, the balloon had a small volume. When the temperature went up, the volume of the balloon went up. A straight line like this represents a direct relationship. Notice the equation looks different. When we had Boyle's law, pressure times volume has to equal a constant. So as one goes up, the other one has to go down. With Charles's law, volume and temperature equal a constant. So as one goes up, the other must also go up in order to equal that constant. So on the next page, we're going to try a sample problem, and we'll use that relationship at constant pressure to investigate. So here we go on our second problem. I've copied over the equation from the previous page so that we can use that. It says a gas occupies 900.0 milliliters. Now they didn't tell you, but you know by looking at the unit that 900.0 must be our volume. So we're going to put volume 1, 900.0 milliliters, making sure to keep all four significant figures. The temperature in this case is 27 degrees Celsius. So our temperature 1, 27.0 degrees Celsius. Now wait, we can't use Celsius, so we have to add our 273.15 in order to get our temperature 1 in Kelvin. That turns out to be 300.15, but we're only allowed to keep one decimal place. So 300.15 Kelvin ends up being 300.2 Kelvin. So that is our answer for temperature 1. What is the volume? That's the question. So we're solving for volume 2, and our new temperature, our temperature 2, is 132 degrees Celsius. Again, we're going to add 273.15 Kelvin. That turns out to be a temperature of 405 Kelvin. No decimal places this time because the 132 didn't have any decimal places. So let's take a look. We're looking for volume 2. Volume 2 is way up here. Two things must be true. It must be on top and it must be by itself. It's already on top, so we don't have to do anything for that. So now the only thing we have to do is isolate it to get it by itself. So we're going to move the T2 across. So our formula is going to be V2 is equal to V1 T2 over T1. Now I can take all my givens and plug them in. My volume 1, 900.0 milliliters. I'm going to multiply that by my temperature 2, 405 Kelvin. All of that is going to be divided by my temperature 1. My temperature 1 is 300.2 Kelvin. So, we said that the relationship between volume and temperature was direct, meaning as volume increases, temperature increases, or in this case, as temperature increases, as it goes from 300 to 405, we should also see an increase in volume. Well, the volume for this problem, volume 2, when you solve for this, turns out to be 1214 milliliters, but because we're limited to just 3 significant figures, our volume 2 is going to end up being 1210 milliliters. Questions? Again, write them down, jot them down, write them somewhere so that when we meet tomorrow, you can ask those questions. Okay, it's time for our third and final gas law. This one represents the relationship between pressure and temperature. If you notice, the relationship looks very similar to what we saw in Charles's law, except the volumes have been replaced by pressure. So, if the equation representing the relationship is the same, the relationship on the graph is also going to be the same. So at low temperature, pressure is also low. At high temperature, pressure is also high. This is another direct relationship. Think about this for a second. If you have a Mylar balloon, the silver ones that you get for people's birthday parties, and you go outside, let's say you buy it in the store, they fill it up with helium, you go outside and it's really cold, it's snowing in fact, and here you are with your Mylar balloon. Well, in cold temperatures, this has a fixed volume, right? So unlike a latex balloon, which you can blow up and change the volume of it, the Mylar balloons have a fixed volume. So the amount of molecules in there is a constant, the volume is a constant. The only thing that changes is when you go outside into cold temperatures, you might notice that it becomes soft. It's the pressure inside the balloon goes down. Once you take that balloon back into your house, let's say you drive it home, you go into your house, the balloon fills up just like it did in the store because the temperature increased, so the pressure inside the balloon also increased. Okay, this is our third and final question that we're going to do today. So this question uses this relationship between pressure and temperature. Volume is held constant. Let's start reading the question. A 12-liter sample of helium gas is confined inside a rigid metal container. That's a clue right there. A rigid metal container, that doesn't change volume. So this 12.0 liters that they gave us, that was a trick. We can get rid of something like that. Volume doesn't change in this relationship, so we can ignore volume. Let's continue reading. Initially at 25.2 degrees Celsius. So temperature 1 equals 25.2 degrees Celsius. I of course have to change that to Kelvin. I have 1 decimal place allowance, so this becomes 298.4 Kelvin. The container is placed in an oven. Not a smart move, but good for this example. I just added that in. If the original pressure in the container, so P1 equals 3.00 atm, what is the new temperature of the gas in Celsius? So temperature 2 is what we're looking for, and notice that it's asking for that in Celsius. I talked about this on Tuesday. If they give you a temperature in Celsius and they ask you for a final temperature in Celsius, it's a trick. You still have to go to Kelvin, do the problem, and then go back. All right, at the last part it says the new pressure is increased, so P2 is going to equal 5.07 atm. This time I selected a problem where the equation is a little bit more challenging to solve. So I have T2 on the bottom. Remember our 2 rules. Has to be on top, has to be by itself. So the very first thing I'm going to do is put T2 on top by moving it diagonally across the equal sign. So T2 is going to end up here. So I'm going to get rid of this, and I'm going to get rid of this. Now I have P1, T1, and I have to get rid of both of them. So T2, that's going to stay on top, and on the left, it's going to be by itself. The T1, which is on the bottom on the left, is going to go up here, top on the right. So I'll get P2, T1 divided by P1. Now I can substitute in all of my values. So my pressure 2, 5.07 atm. My temperature 1, 298.4 Kelvin. My pressure 1, 3.00 atm. ATM on top, bottom, those drop out. I'm left with an answer in Kelvin. So when I solve for this, temperature 2 ends up being 504 Kelvin. Now, let's think about this for a second. The relationship between pressure and temperature is direct, meaning as one increases, the other increases. So we went from a pressure of 3 to a pressure of 5. Pressure went up. That means temperature should go up. We started off at a temperature of 298. We finished with a temperature of 504. The last part of this problem, reminder, is to go back to Celsius. So now, to go back to Celsius, we're going to subtract 273.15. So our temperature 2 in this case turns out to be, no decimal places, 231 degrees Celsius. This, 231 degrees Celsius, is our final answer. And if you're wondering, that equals about 450 degrees Fahrenheit. So totally within the realm of what you might set your oven temperature to be. Okay, finishing up. So we have 6 homework problems tonight. The assignment looks like this. There are 25 homework problems here, or 25 problems here. We're only going to do 6. So please go back to the very first slide in this presentation and make sure you make note of the 6 problems that I would like you to do. I selected 2 of each of the 3 types of the gas laws that we learned today. Thank you very much, everyone. Please try the homework problems. If you have questions, I'm going to try going over them with you tomorrow on the Zoom session in case you have any questions. Thanks so much. Bye, guys.